Hello, everyone. As you all know, my name is Anya Vostinar, and I teach at Carleton College. And I will now be talking to you about my software, Symbiosis, which is an agent-based simulation of symbionts. So the outline of my talk, first I'll talk about why such software might be useful, then I'll talk about how it works, some previous results that I've reported on, and future directions I'm thinking of, and some questions that I have for you. So I don't really need to remind this group, but just to remind ourselves, we now know that symbionts, especially microbial symbionts, are found nearly everywhere that we look. And if these New York Times headlines are anything to go by, the public is fascinated with how such symbionts might affect human health, might affect the world. But I want to draw our attention to this last headline. In some cases, even bad bacteria may be good, which really illustrates that symbionts aren't strictly parasites or mutualists. They can change between those. And we want to look at the various ways in which they do that. So context dependence is when a symbiont changes whether it's a mutualist or a parasite, depending on the environment. And so this can happen because of a number of reasons, but one main example is that there might be this purple resource that the host needs. And so if we're in an environment where there's no resource available and the symbiont produces that resource in exchange for some sugar that it takes from the host directly, then this can be a mutualist because the symbiont is providing something of benefit to the host. However, if the host happens to be in an environment where there's plenty of purple triangles for it to take in itself, it doesn't need the symbiont anymore, but the symbiont is still producing purple triangles and then taking sugar, just exactly the behavior it was doing in this other environment. But now this symbiont is actually a parasite because it's taking sugar, something else important from the host, and it is giving nothing in return, nothing useful. So this is an example of where ecological changes can actually change the definition of what a symbiont is. In addition, symbionts, like everything, evolve. And often they can evolve faster than the host because they might be smaller than the host, or if they are smaller. And they can evolve in many different directions. So we really need to think about parasitism and mutualism and commensalism, where the host is not affected negatively or positively by the symbiont, as this spectrum. And the symbionts can evolve along this spectrum back and forth, and understanding what factors lead to movement along this spectrum is important. So this is where artificial life tools can be really useful in understanding these sorts of ecological and evolutionary dynamics in addition to wet lab work. However, many artificial life systems are built to focus on a single sort of level of living. So there's a population of organisms, and they may even eat each other or cooperate or do lots of different ways of interacting, but they are all just living in the population kind of at the same level, whereas symbionts often live inside of their hosts, called endosymbionts. And so if we want to study those sorts of dynamics, it's not going to work in this existing system. And adding to these sorts of systems can be rather difficult, trust me, I've tried. And so to look at these questions that interest me, I built a new agent-based system called Symbiosis that's built with symbionts as the focus from the ground up. So I'll show in a minute how that looks exactly. But another assumption that I made was that symbionts should be able to evolve between parasitism and mutualism. We should consider it this spectrum as a fundamental assumption. They aren't just bucketed as just a parasite, because otherwise I can't study the questions that interest me. And I wanted to start with as simple a model as possible so we could look at what dynamics are even seen in that sort of a model, and then add features as they're necessary to explore additional questions. So what this looks like, so I have a population of hosts, and an individual host has just a single number, its interaction value, that determines all of its behavior. And then similarly, the symbionts have a single number that determine their behavior. And so if the number is negative, between -1 and 0, then that represents an antagonistic relationship. So the host is investing a portion of its resources into defense, and the symbiont is trying to steal those resources, and the amount more negative it is how much it's able to steal. And then if the numbers are positive, that means that there is a mutualistic relationship. The host is donating that proportion of resources to the symbiont. The symbiont donates that proportion back to the host. If that was the end of the story, though, there'd be no reason for the host to engage in this behavior. And so there is a synergy factor that is applied. So the amount that the symbiont donates back is multiplied by 5. And this is an abstraction of the various ways in which symbionts are able to do things more efficiently than the host, or do things that the host can't do. So either like maybe digest a resource that the host can't digest, or provide defense that the host can't provide on its own. So it's doing something that the host can't do on its own. And that's what's kind of captured there. And then symbionts have 2 different ways of reproducing. They can vertically transmit, where their offspring are, they have a certain chance to get their offspring into host offspring when the host reproduces. And then they can also horizontally transmit, where they just copy themselves and then send their offspring off into the world to infect another host. So with those 2 things in mind, I looked at how vertical transmission rate interacts with spatial structure. So there, I just, in this, I have this nice GUI that you can actually go and use for yourself. I'll have the link at the end. But you can set the vertical transmission rate between 0 and 1, and then you can also set the reproduction. So there can be global reproduction, where when an offspring is born, it is sent anywhere in the world, kind of representing like well-mixed media. Or it can be local reproduction, where the offspring just goes into the immediate neighborhood of the parent. So as if like they're on like a biofilm or something. And so with these 2 different settings to tweak, you can actually run all of my experiments for yourself in the GUI. This isn't a toy version of my software. This is actually my real software running in your web browser, which I think is really cool. And I found lots of different things, but one of the most interesting that I reported in this paper last year was that local reproduction actually leads to parasitism, where global reproduction will lead to mutualism at this 50% vertical transmission rate. This is true for kind of the neighboring vertical transmission rates as well. And so this was interesting because oftentimes we find in cooperation literature that spatial structure increases the amount of cooperation. That is certainly not a universal rule. There's lots of exceptions, this being one of them, where because of the symbiosis and reasons I'm happy to talk about further if you're interested, the spatial structure actually decreases the amount of cooperation that is found. I have a number of different things that I'm interested in pursuing still. So I've added multi-infections, so there can be multiple symbionts within a single host. And I've also added a lytic life cycle. So I'm very interested in how bacteriophage, which are viruses that infect bacteria, how they interact with their bacterial hosts. And so lysis, the lytic life cycle, is one way that bacteriophage reproduce. And so with that implemented, I'm now looking at the ratio of phage to bacteria and how that changes over the course of time. And it turns out that it changes in very unpredictable, kind of unintuitive ways that I'm happy to talk about my investigations into what's actually going on here. But so that's interesting, since phage are trying out being used for fighting various antibiotic-resistant bacterial infections. And so understanding how their ratios change over time can be really important for that sort of work. I'm also working on adding more complex genomes, basically like the other end of the spectrum in terms of complexity of genomes. For those of you familiar with Avida, this would be Avida-style genomes, where they are Turing complete and are able to do any behavior that a computer is able to do. And then also adding multiple different resources so that we can see division of labor between hosts and symbionts. Improving the web GUI to show multiple different symbionts within a host. This is a really difficult visualization problem, so if you have ideas, please let me know. And then adding various other bacterial viral behaviors to study those sorts of bacterial virus systems better. So my questions for you all, what behaviors of hosts and symbionts do you think are most important to add next? I really want to hear what ideas you all have. And in particular, I want to know what would be necessary for software like this to actually be useful to you. I would love to see this sort of thing used to answer other questions of interest and want to know what would be good for that. As promised, Symbiosis is available at symbiolation.com. And then I'd love for you to follow me on Twitter and we can discuss it more there. Thanks so much. Bye.